Okay, so I guess everyone here is from the civil engineering background or no? You have people from different areas. Everyone is from civil engineering, right? Or mechanical and civil engineering. Okay, so as I said earlier, this course is engineering mechanics, and typically we will be focusing on the statics part. So typically you'll see some sort of a quick introduction like this. So the static part, we just consider bodies that are at rest or moving with a constant velocity, because they are a lot easier or a lot less complicated compared to other components. So for example, maybe the first problem you deal with is statics, and then you move on in the future, you can think about the material mechanics, that is the behavior of the material itself. And then we also do structural analysis, and then we also consider the dynamics part. Maybe you have earthquakes or the body is moving. So this one, the analysis is time dependent. And then from there, we also do more in-depth analysis. For example, the RC design, reinforced concrete, steel design, wind engineering, which is also quite complicated because it involves a lot of dynamic activities. You have the wind, you have the waves, whatever. And then also structural system design, advanced RC design, also a little bit more complicated than the RC design. And then you move on to another component which is even a lot more complicated. We have the structural matrix analysis, pre-stressed concrete, advanced steel design. So all of these are very integral components for civil engineers. But to better understand all of this, you need to start from somewhere, which is the statics part. Okay, and so here we just have a few structures, and then it talks about engineering mechanics and statics. Why is engineering mechanics important? Because whenever we build structures, the structures are always subjected to various forces. Every structure will be subjected to forces. But then you want to ensure that the structure that you build will stay stand still, even if it is subjected to forces. Otherwise, if the structure cannot sustain the forces that are acting on it, what will happen? It will just collapse. And that is the last thing you want to happen as an engineer. Okay, so typically for this course, this is the outline. So we have an introduction, that is the general principle, and then we will talk about force vectors. We also talk about the equilibrium of a particle, force system resultants, equilibrium of a rigid body, structural analysis, internal forces, friction, center of gravity and centroid, and also the moment of inertia. So these are the 10 major components that we will be discussing in this class. And for the coming weeks, we will be going through each of these one after the other, one by one. Okay, and this is the book that's been recommended by the professor, Engineering Mechanics Statics in SI Units. So this is the 14th edition, and this is the one that the Professor Lee will be using for this class. I think if you want to get a look at this book, you can probably go to the library and then try to borrow one, or you can read it there. It might be a little bit expensive to buy one just one semester. Okay, so here he just wrote down how the grading system is going to be for this class. So 20% of your grades will be from your assignments. So the assignments are always very, very important. Please make sure you always submit your assignments on time. If you cannot, then you try to talk to the TAs and try to explain to them as to why you cannot submit on time. And then maybe they will give you a little bit of time to finish it. But then also don't make it a habit that your assignments are late every other week. Okay, and midterm exam 1 will go for 25%, midterm exam 2 will go for another 25%, and then the final exam is 30%. So as I said earlier, you have 2 midterm exams. Okay, and for the assignments, it's just 1 week to complete an assignment. So since the classes are on Monday and Tuesday, typically if you finish the class on Tuesday, you'll have an assignment, and then you will expect to submit it by the following Tuesday. That is 1 week for you to finish the assignment. Okay, and then this is the email address for Professor Lee. So if you want to get in touch with the professor, or you cannot come to class or anything, you can email him on this email, and then he'll get back to you. Okay, and I think this one is just more like what the professor expects when you solve your problems. Okay, so when you are solving a problem, it is important to include the units. So, for example, you are solving a problem, is it in kilograms, is it in Newton, is it in seconds, is it in milliseconds? It is important to state which unit you are working in. And then also, he mentioned, okay, you get the right answer, but sometimes you may get the right answer, but then if you don't indicate any unit, you may lose some points. It is important to tell the person you are solving a problem for to know which unit are you working in. And then it also mentioned that if the coordinate system is needed, it must be defined first. So sometimes you are going to work with a coordinate system, maybe XY coordinate or XYZ coordinate, so it is important for you to state which coordinate system you are using to solve your problem. But all these things will be talked about in detail as we progress through this course. Okay, and it's also, if vector is used, the arrow must be shown above the letter. So when we talk about vectors, they will have the magnitude of the vector and also the direction of the vector. So you need to put the arrow on top. Where is the direction of the vector? Okay, so as we progress through the course, we will see all this. Okay. So far, do you have any questions about the course outline, the material, the grading system? If not, we can just quickly go to chapter 1, which is the general principles of engineering mechanics. Okay, so we start with the most basic part. It says the mechanics can be divided into 3 branches. So we have 3 major branches for mechanics. We have the rigid body mechanics, we have the deformable body mechanics, and the fluid mechanics. So when we talk about rigid bodies, we are talking about bodies that do not change their shape or volume when you apply an external force onto them. I mean, in reality, it is hard to say that any body is actually 100% rigid. Any kind of body that you exert a certain amount of force, you will have some certain level of deformation. But to make our problem solving easier, we consider bodies to be rigid when the change of shape or the change of volume is very, very minimal compared to the overall size or shape of the material. So when we're talking about engineering mechanics, the statics part, mostly we will be dealing with rigid bodies. We assume that the body is not going to deform. It's not going to change shape because of the force we put on it. And then for the deformable body mechanics, these are bodies that will actually change shape, or their volume will change when you apply a force onto them. So if you are going to solve problems for this, then it will be a little bit also more complicated than this, because you have to consider the effect of the change in shape. And then we also have fluid mechanics. I'm not sure if any of you have taken the course in fluid mechanics yet. Okay. So it's also another component. Fluid mechanics mostly talk about like liquids, or it can also be gas. Okay, so we have here, when we talk about rigid body, then they can be divided into 2. That is the statics and the dynamics. So for this program, we are going to focus on the statics component. That is the bodies that are not moving, or they are moving at a constant speed. Okay, and the dynamic ones are the bodies that are moving or subjected to some sort of acceleration. But this is not within the scope of this course, so we will just focus on the static bodies. Okay, so here it says the mechanics. We have the rigid bodies, deformable bodies, and fluids. So we have the incompressible and the compressible fluids. So incompressible may be more like water. You cannot change the volume by applying pressure on it. But the compressible fluids are like gas. If you apply some sort of pressure into it, you can change the volume of those materials. And then we come here, what we need to focus on in our program, that is the statics part. We don't expect our bodies to change shape. So we are mostly focusing on the forces that are acting on the material we are dealing with. Okay, so here it says, when we talk about statics, we are talking about equilibrium of bodies. Equilibrium of bodies means that the body is at rest. So that means the body is not moving. It is at rest, like this building is at rest. Or it moves with a constant velocity. So maybe the body is moving, but the velocity of this body is not changing. Why? That is because there is no unbalanced external force on the body. If there's an unbalanced external force on the body, then we will experience some sort of acceleration. If there's any sort of acceleration involved, then the body is no longer static. It will become dynamic. So we are only dealing with at rest, and if it's not moving, or the velocity for this particular body is constant. Okay, so here it talks about trying to give a brief difference between statics and dynamics. So it says the principles can be formulated simply from measurement of geometry and force. So you can just look at the material geometry and then the force acting on the material, and then you can use statics to solve those problems because you assume that the shape of the material, the volume of the material is not changing over time. It is not subjected to any outside acceleration. But for dynamics, the material properties may be changing. There might be changes in the way the material is moving, like a change in velocity. So it depends on accurate measurement of time. So the behavior of the material at different points in time can actually be quite different. So you need to be able to capture different time periods. So that's why this one is easy. You just capture one and then you can solve a problem using that one geometry and force. Whereas for this one, you need to focus on different time steps. Okay, and next we can look at the idealizations, that is the fundamental concepts of engineering mechanics. So we will look at particles. Okay, so when we talk about the particles, we can consider the mass but neglect the size. So what do we mean by that? For example, when we talk about the size of the Earth, we can think of the Earth as it is very, very big. From our perspective here, it is huge. But it can be considered to be insignificant if you try to compare it to the size of the orbit. Because the size of the orbit itself is a lot bigger than the size of the Earth. So this we are talking about in relative terms. For example, you say it's very big. Someone may be, how big? So you need to have like some sort of relative judgment. Okay, the size of the Earth is very big. Okay, let's compare it to the size of the orbit. Then it's not big. So this one we consider the mass, but we neglect the size because the size is too small. And then when we talk about rigid bodies, now the rigid body is a combination of large number of particles. Okay, so we will have a combination of large number of particles, and then we consider that to be a single body, but we will not care much about the material properties. So it says we neglect the material properties. So you don't need to focus about what are the material properties for this particular thing you are dealing with. You just consider the forces acting on it, and then you consider the material to be a single body. Okay, and another thing that we may or we will see a lot in this course is the effect of is the concentrated force. So we have different types of forces. When we solve problems, typically you may see something like this. And maybe this is. But in some cases, maybe you have something like this, and then Okay, so we have the concentrated. You have a large body, but the force is just acting on one single location. And this one is more like that, distributed. The force is distributed over an area. But in this course, most of what we'll be dealing with will be concentrated forces. Okay? So the concentrated force, we assume that the force is going to act on a point on the body. For example, this is the railway line, and then this is the wheel. You can assume that most of the force is acting between the point of contact between the wheel and the railway line. So we can consider this to be a concentrated force. Alright? So represented by concentrated force, provided loading area is small compared to the overall size. Okay, so just like here, the overall size is big, but we assume that the force is mainly just acting at this point and not like this, not all across the material. Okay, and another fundamental concept that is very important in this course will be the laws of motion by Newton. That is the 3 laws of motion. So we have the force law, that is the law of inertia. That is a particle originally at rest or moving in a straight line with constant velocity will remain in the same state provided that the particle is not subjected to an unbalanced force. So if this particle is here and then you don't apply any sort of force onto it, it will remain like that until you do something to it, maybe apply a force, then the particle will move. And then another thing it says is that the particle will remain in a constant velocity. If it is moving, then it will move at a constant speed unless it is subjected to an external force. And this is why the second component here is also very important. That is the second law of inertia. A particle acted upon by an unbalanced force experience an acceleration that has the same direction as the force and the magnitude that the direction is proportional. So here, this is the particle, you have a force, and then the force hits this particle. So the particle will move in the direction of the force. So this is why we have what F is proportional to A, and then F is equal to ma. And this law also explains why it's easier for you to push a bicycle than to push a car. Because you can understand, if you want to keep this constant, let's say you want to have an acceleration of 1 meter per second square, and how much force do you need? Maybe the bicycle, the force will be, or the mass is only 10 kg, and then you assume that, okay, for the car, this is 1000 kg, and how much force do you need to get this? And then how much force do you need here? So this law simply explains that. Why we can, maybe only one of us, I think everyone here can push a bicycle, but we may need like 10 of us to push one car. Okay, and the third law of motion, the mutual forces of actions and reaction between two particles are equal and opposite and collinear. So what this says is that to every action, there's an equal and opposite reaction. It's also the reason why when you get a basketball and then you throw it to the wall, the ball will just come back to you. Okay, and we also have the Newton's law of gravitational attraction. So this is like the force of attraction between particles in a space. So we have F equal to G. So this G is the universal constant of gravitation. And the M1, M2, we consider two bodies of masses. Mass 1, mass 2. And then the R is the distance between the two particles. So we will have F, that is the force of gravitation between the two particles here. So this is also Newton's law of gravitational attraction, that is the force of attraction between particles or two masses within a space. And this is important, particularly when we try to get the weight. Okay, so we say W here means weight is G, and then the mass of this material, and the mass of the Earth. And then this R square is the distance between the particle we are dealing with and then the center of the Earth. So this here, the G yields something like this. This G, ME, mass of the Earth over R squared, that is the distance between the particle and the center of the Earth. So W here is equal to mg. So the G is more like a representation of this volume. And this also explains why when we measure the mass of things at different places, we might get different volumes. If the weight, even though the mass may be the same, but when you measure the weight in different locations, the weight might be different. Okay, so here it says F to get the force is the M, that is the mass multiplied by the G, which is the acceleration due to gravity. And it says since G is dependent on R, so we saw that here, the acceleration due to gravity, G here, is dependent on R. So the weight of a body is not an absolute quantity. It's not fixed. It can change depending on the location because G depends on R. And the magnitude is determined from where the measurement is taken. Okay? So it says for most engineering calculations, G is determined at sea level and at a latitude of 45 degrees. This is if they are trying to get very, 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 very accurate measurements. But in practice, for the most common things, we typically will not follow this. Okay, so here is just an example. It says the astronaut's weight is diminished in space. Why? Because the astronaut is actually very far removed from the gravitational field of the Earth. So that R is very, very huge. It's too big. So the value of G is significantly smaller. So if the value of G is significantly smaller, then weight will become really, really, really small too. Okay, and here we also have the international system of units. So basically, for this course, most of the units you'll be using will be mostly these three. Okay, so we have the unit for length, the SI unit that is meter, and then the time we have second, and then for mass we have kilogram and kg, and then force can be represented in Newton or kg per meter per second square. So for this course, we are typically going to be using SI units. So most of the units you will see, and most of the units you will solve problems in, will be represented in either meter, second, or kilograms. Or you can represent them in force meters in Newton. Okay, and here we just have the standard value for G. It says at the standard location, G is equal to 9.806, and then meters per second square. And then for calculations, we will just use to 2 decimal places, 9.81. This is good enough. Like if you're solving a problem, just 9.81, you stop here, it's good. You don't need to really waste your time to write all the decimal places. Okay, and thus W is equal to mg, so the G is 9.81 multiplied by m. And hence a body of mass that is 1 kg will just have a weight of 9.81 Newton, and 2 kg body will have 19.62. So we just stick to this unit. Whenever we need to use G, just use 9.81. Okay, and here also these are some of the exponential forms that you may see throughout this course. So for example, when we talk about giganewton, it will mean what? The Newton value should be in 10 raised to the power 9. Okay? For example, maybe the question, instead of just writing it, will say 1 giga. So when you're solving the problem, you just know that, okay, this should be 1 times 10 to the power 9 Newton. So some problems, instead of writing down the whole unit, they may just use this prefix to describe it. Okay, so when we talk about giga, it means 10 to the power 9. Mega is 10 to the power 6. Kilo will be 10 to the power 3. So you might see a lot of problems that will give the values in kilonewton. So if you're solving problems, then you need to remember to put 10 to the power 3, or you may not get the right answer. And then these ones, at the bottom, we just have the negative value. So we have the milli, 10 to the minus 3. The micro is 10 to the minus 6. And nano will be 10 to minus 9. And then these are the symbols. Okay? So it is important to remember this, like either this or this. Because of some problem definitions, you may just see micro-newton or m-newton. So you need to know that this is actually 10 to the power 6 to the minus 6. This is 10 to the minus 3. Okay? It's not that complicated, but you just need to familiarize yourself with the table. Okay, and so here it's just trying to tell us the rules for use of the units. How do we use the units appropriately? And it says quantity is defined by several units, which are multiples are separated by dots. So for example, this can be separated by dots. So the kg dot meter dot second squared. But I think typically if you can just write this, you should be totally fine too. But this is like the most conventional approach. Okay, this is the conventional approach. And it says the exponential power represented for a unit having a prefix refer to both the unit and its prefix. So for example, here we have the micro Newton, and then to the power 2 typically can be written like this, micro and Newton. All can be squared. Okay, and here we just have some recommendations on how you can appropriately use the units. So it says, with the exception for the base unit, the kilogram, in general avoid the use of prefix. So the prefix is like the prefix in the denominator of a composite unit. For example, we have here Newton per millimeter, but the base unit is meter, not millimeter. So you can try to change this Newton to kilonewton and make sure that the denominator, that is the value of at the bottom, is in meter. So our base units will be meter, kg, and second. Or here we have m per mg, milligram. So mega, and then we change these to the milligram to kg. So it's like just a suggestion or a recommendation that engineers will usually or typically follow. That is to make sure that the value at the bottom is in the base unit, not a prefix. Okay, and it says in calculations represent numbers in terms of their base, or drive units by converting all prefix to the powers of 10. So if possible, you can just write the values to the power of 10 instead of writing very, very long numbers. Okay, so this is just an example. So it says you have something like this, 50 kilonewton per meter and then 60 nanometer. So here, 50 kilonewton per meter, you change this to just Newton, right? And then 10 to the power 3, and then 60 nanometer, 10 to the minus 9, and then you make sure that this is in the base form. And then when you write the final answer, you make sure this value is in meter, and then this one also is in the unit form. But the most important thing here is this. The denominator here is in the meter format, so they are all in the same unit. So the final result should be expressed using a single prefix, okay? So you have to make sure that your units are the same, or the prefix for the units are the same. Okay, and the next one we can move on to the numerical calculation part, that is the dimensional homogeneity part. It says each term must be expressed in the same unit, and all the terms of an equation can be combined if the numerical values are substituted for the variables. Okay, and then regardless of how the equation is evaluated, it is maintained in dimensional homogeneity. So for example, when we are trying to find the distance here, and then we say velocity times time plus half the acceleration times the time squared. If you want to ensure that this value you obtain is in the right unit, that is meter, you have to make sure what? All the values here are at least in the same unit, right? So the time should be in second, the velocity meters per second, and acceleration is in meters per second squared. So you need to make sure that you are working in the same unit in order for you to arrive at a reasonable answer. Otherwise, if you, okay, let's say the time is in minute, your velocity, okay, meters per second, and the acceleration, you say millimeter per second squared. At the end of the day, the answer you will get is not going to make sense. It's because you are using conflicting units. So you need to make sure that when you are using your units, they are all in agreement, okay? Okay, and here it says the significant figures. So it's just about the number of significant figures containing any number determines the accuracy of the number. So the more significant figures you have, the more accurate the solution is, but you also don't want to have too many. Then it will not be ideal, or it will not be reasonable. So it says, for example, we have this, we can just use 4 significant figures, we can use 5 significant figures, depending on how big or small the value is. But here we have a question, it says, if zeros occur at the end of a number, then how do we overcome this repetition? So for example, maybe you have something like, okay, like with a lot of zeros. As an engineer, you probably don't want to repeat the process of writing so many zeros, right? So how do we solve this problem? So that is where the engineering notation comes into play. And what is the engineering notation? It's that the numbers be rounded off to the appropriate number of significant digits and be expressed in multiples of 10 raised to the power 3. So if you have a lot of zeros, so you can express the number by saying, okay, 10 raised to the power 3, or 10 raised to the power 6, or 10 raised to the power of 9. So this is the recommendation based on the engineering notation system. Okay, so you can use the multiple of 3 format. And if the number also has a lot of things, let's say 0, 0, 0, 0. Okay, a lot of zeros at the beginning, you can also still do the same thing. Use the multiple of 3 notation to write it down in a more proper format. Okay? So here we just have an example. It says 5 significant figures. Okay, so you can write it down to three significant figures, 2.23.4, and then 10 raised to the power 3. And then you get the same thing. Okay? So it makes it a lot easier to typically read the read the work you do, but also in the future, even if you go to work outside, because maybe you read a report or you write a report and then you need to give it to someone else. If you are working as an individual, you may think that, okay, whatever I do is fine, I can understand it. But if you are working in a big company, probably you have to share what you do with 10, 20 people. So it's like not everyone should follow your standard. It's more like we have one standard in place that we all follow so that it's easier for everyone to understand what the other person is doing. Okay, so that one is also the same thing, just trying to tell you, if you have zeros at the beginning, you can just do the same thing, right? So if to three significant figures, we can just 1, 2, 3, and then 8.21 times 10 to the power 3. We just have three significant figures here. And then the same thing here. If we want to use this, we can just up to here, 1, 2, 3, and then 0.582, 10 to the power 3. Or we can go 1, 2, 3, 4, 5, 6. You just use these three significant figures and then 10 to the minus 6. Okay, this one, the rounding of part, I don't think should be a problem. It's typically okay, so these are all still recommendations. They say do not round up the calculations until expressing the final results. Until you want to express the final value, it is not very advisable to round up the numbers to very, very small values. Okay, so you can still round up because if you have like 2, 3, 4.07567, that's still too long. You don't want to use it in all of your calculations. But to do the final rounding up, it is much more advisable to do that when you are writing down your final result. And then this is also another, it's just what is happening in the book. So it says in the book we will round up the answers to three significant figures. So you can use that same standard when you do your assignments or your midterm exams or the final exams, is that when you're writing your final answer, you can write to three significant figures as well. Okay, so here is just a very basic thing. It's just trying to tell you, like trying to familiarize yourself on how to convert from one unit to the next. Convert 100 kilometers per hour to meters per second and 24 meters per second to kilometers per hour. I guess by now everyone should be pretty familiar with the unit conversion system, right? So we have 100 kilometers per hour, so we change the kilometer to meters, right? So 1,000 meters make 1 kilometer, so we get this here. And then we change the hour to seconds. In 1 hour, we have 3,600 seconds. So this goes out, this goes out, and then we just use our calculator, and then we comes down to this. And then the same thing here. You have to convert this to kilometer per hour. So we have meter, 1 kilometer, and the meter is 1,000. 1,000 meters is 1 kilometer, and then here, second convert to hours. And then we also get the same value here. So it's like some very basic transformations that you need to do. Okay, or if you don't want to do it like that, you can just convert the 24 meters to kilometers directly, divide this by 1,000, and then you change the second to hour. Okay? Vice versa, whichever you find easier. Okay, so here we have a similar thing. It's asking us to convert the density of steel, which is 0.85 gram per centimeter cube to kilogram per meter cube. So we know that 1 kg is equal to 1,000 grams and 1 meter is equal to 100 centimeters. And arrange the conversion factor in such a way that G and cm can be cancelled out. So we have 7.85 gram per cm cube, right? So we first need to conversion from this to this. So 1 kg divided by 1,000 grams, and then we know that this is this, and then you just follow the same simple approach. And then here it is important to remember the cube should be for both. Because the centimeter is in cube now. We know 1 meter is 100 centimeters, but then you need to make sure this value is in cube. Otherwise, the result you will get will not be correct. Okay, do you have any question with what we have gone through so far? If nothing, we can have a break. Okay. All of you are able to access the module, right? Yeah. As far as you can log into the module, like immediately after the class, the PowerPoints will be uploaded into the module, so you can just access them from there. You don't need to worry about that. Okay. So I think for the next hour we can move on to do a little bit more handiwork, forces and vectors. But before that, I think the unit conversion, everyone is quite okay with that, I assume. I think the only thing you need to pay attention to is, for example, okay, you say, okay, 100 centimeter, make 1 meter, and now you want to convert cm cube to meters cube. So sometimes that's where the confusion for some people might come into play, right? So if you are going to do this conversion, you have to make sure that if you want this to be in cube, then everything here should be in cube, and then here also should be the same thing, right? So it's no longer 100, but the 100 plus this. It will be 100 raised to the power of 3. Alright, so that's the only thing you need to pay attention to the conversion part. Other than that, I think everything else should be quite straightforward. Okay, so if no problem, we'll just move on to the forces and vectors, and hopefully we can just explain that a little bit in detail, and if possible, we can finish a little earlier too. Okay, so here we'll just quickly go into chapter 2, which will talk about the force vectors, and before that we'll just give a quick recap or definition of what is scalar and then also what is a vector. Okay, so a scalar, it says, is any positive or negative physical quantity that can be completely specified by its magnitude, that is the size. For example, you can measure something by its length. Like you can say 10 centimeter, okay, 10 centimeter, but in which direction? It's just 10 centimeter, 10 centimeter. Mass, maybe in kg or grams, and also time, like second, okay? So the scalar will just give us a magnitude. It just tells us the size. So what is the major difference between that and a vector? Okay, so typically for this program, or this course, what we will be dealing with is like most of what we will be solving problems on will be vectors. We will be using vectors, okay? So a vector is any physical quantity that has both a magnitude and a direction, okay? You know where it is pointing to. For example, you have a force, okay? 100 kilonewton, okay, 100 kilonewton, which way? X direction, Y direction, this way, that way. At least you need to know, okay? The position and also a moment. Okay, so it will give you both a magnitude and a direction. Okay, so it says a vector is shown graphically by an arrow, and the length of an arrow typically will signify the magnitude of the vector. Okay, so if the arrow is much longer, it is signifying that the magnitude of this vector is larger than the other one. Okay, and the angle theta between the vector and the fixed axis, that is the direction of its line of action. Okay, so we may have a fixed line of action here, and this is theta, and then maybe this is the vector A. Okay, so this one is the direction of the line of action from the x. And the arrow is the sense of direction of the vector. So here you can see our arrow is pointing this way. Okay, so here this angle will show us what? The direction of the line of action. And then this arrow is the sense of direction of the vector. Which way is the vector pointing to? Okay, so here, this is just an example. It says magnitude of a vector is like it has 4 units. So it assumes that each of these is a unit. 1, 2, 3, 4. This is our vector. Okay, and the direction of the vector is 20-degree measured counterclockwise from the horizontal axis. This is the horizontal axis, and counterclockwise. We have the clockwise direction and the counterclockwise direction. So counterclockwise, 20 degrees from the horizontal axis. So this is this way, and this is 20 degrees. And the sense of the vector, upward and to the right, is upward and to the right. So this is the sense of our vector. Okay? So this, we know the sense of direction. The vector is pointing this way, and then we also know, based on the length of the arrow, we know what is the magnitude of this vector. Okay, it says the point O is called the tail of the vector. So this is the tail, the starting point. And the point P is called the tip. That is the head of the vector. So this vector will have a tail and a tip, or the head. And then we have this direction, and we also have the angle here. So most of the problems that you will be dealing with, you will always see this: an angle, a magnitude. Okay, you have an angle and a magnitude. Okay, and as we stated, it says the size of a vector can be represented by what? The length of the arrow. So this is A. The magnitude for this is A. And the size of this line, in our imagination, this is twice the size of this. So what will be the size of this? Then it will be 2A. Because in our world, we already believe that this vector can be represented by the length of the line. Okay? And now, something interesting. It's no longer A, even though the sizes are the same. But it is what? Minus A. Why? That's because this and this are in opposite directions. Okay? So they are in opposite directions. It's the same thing like sometimes when we solve problems. For example, this is a body here. Okay, and then we assume, okay, our x-axis, our y-axis. And then we assume, okay, any force acting here might be positive. If we assume, or we want to assume that this is positive or negative going this way, then we have to assume that this way will be positive. You cannot say this is positive and this is positive. You have to choose one. So it's the same thing that is happening here. If we say that this vector is A, and this one is going in the opposite direction, and it is the same size, then it's just negative. Okay? And then this now is half of this. So it's half of A minus, okay, the same thing. Okay, so here we have the vector addition, and this is the parallelogram law. So we have two vectors, that is A and B, and then they are going in this direction. So we have A this way and B going this way. We can put them together, right? Okay, so since this is our resultant vector, so the combination of the resultant vector R will be like A plus B. And in some cases, we can, when we solve problems, we can just write this like this. The B, because it's going this way, we can just bring it here. It's the same thing. You just move it. With this also, okay. Okay, so that's just what they did here. That's the triangle rule. So it says R equal to A plus B. You have A here, but B is going in this direction, so that means this, you just move it here. And then this and this will give us the resultant. Or if you want to do it another way, you say, okay, I want to keep my B fixed, but I want to move the A to come here. So that's how you get this. And then we still, so either this way or this way, they're all fine. It depends on how you want to work around the problem, or whichever way you find most ideal for you. They're all right. Okay, so here it says the vector subtraction. That's the special case is R is A and then minus B. Okay, so how do we get A minus B? So here, we still keep this vector. It's here, A is moving this way. It's fine, but originally this B was pointing in this direction. But if you remember earlier, we already mentioned that we can change the direction of the vector, but the magnitude of the force will become negative. So here what we just did is change the direction, okay? But the magnitude still remains the same. So now this is, instead of B, it is minus B, okay? So you can have something like this. And then if you want to make it a triangle, then this one will become this. And then the minus B, we just bring it here. And then we still have this in place, okay? So you can play around with the vectors, you can move them in different positions, and then you can apply the triangle construction law or the parallelogram law to solve the problems. Okay, so I think this is more representative of what we will be seeing a lot of problems like this. Okay, so you may have one force here and another force here, and then they will try to tell you to find the magnitude and the direction of the resultant force. You will come across a lot of that. And just as we did earlier, it's like, okay, it's still the same thing. Here, here, and then we expect the FR, that is the resultant force, to act somewhere here. So it's the same thing. You just assume this comes this way, this comes that way, and the resultant force is here. They will be at some point. And then the F2, you just can move it here to follow the triangle law. And then F resultant will be this in combination with this. Okay, F1 plus F2. Okay, and we also have another one is that we can resolve a force into two components. Okay, maybe we are not given this. We are also not given this, but we know our resultant force. And now we need to find what is the force along here and along this line. Okay, so that is also still very, very possible. We can just, the same thing here, we have the FV, FU, just follow the same rule, you draw a triangle and then you use the same relationship. You can get this and this. Later on we will see the relationship between this, and the angles here. It's not all that complicated. Okay, so as we've seen earlier, whenever we have problems with vectors, we try to make them into triangles. The reason for that is that once we are able to idealize and represent the vectors in a triangle, we can use this law, which is very simple and straightforward, to solve the problem we have. So that's why earlier, like after representing all of the vectors, we try to make sure that the end product is like a triangle. So here. And the reason for that is finally here. Okay? So it says the magnitude of the resultant force can be determined using the cosine law. So we combine A and B and we want to find the resultant force, which is C. How do we do that? We will use the cosine law. Okay? We already know A, we already know B. Okay? So we just need to know what's the angle here. Right? 2AB cosine C. We only need to know this angle and then we can know what is the magnitude of the resultant force here. Right? And then we also have the sine rule. I think these two rules everyone is quite familiar with. Okay, so for the sine rule, we assume A, that is the magnitude of A over sine A, should be equal to B over sine B, which should also be equal to C over sine C. So if you want to find any of the direction here, which should be C, then you can just use this, and then the magnitude, you can use the cosine law to find it. So this is why it's important, like whenever we are working with vectors, to try to represent them in a triangle, and then we can use these two laws to solve the problems. Okay, so here we have this. It says the screw arm in figure 2-11A is subjected to two forces. We have F1 and F2. Determine the magnitude and the direction of the resultant force. So we will know that the resultant force is going to act somewhere here, right? We have to determine the magnitude and the direction of the resultant force. So first, Okay, so this is the same representation we have here, right? So we have the F1 along this direction, we have the F2 along here, and then we can have our resultant force here. But the same thing, if we want to use the triangle law, what do? We just move the F2 from here to here. You just transpose it. And if you look at, let me see, the next slide, that's just what they did. Just move this from here to here, okay? Just move it to here. Okay, and another important thing we need to know is that we need to find this angle. To use the triangle law, because you need to find both the magnitude and the direction. So you at least need to know the angle here because the resultant is here. And how do we determine this angle? Okay, so you can look at here. We have this, and this should at least be 90 degrees, right? The difference between here and here. And then we know that here is 15 degrees. Here is 10. So how do we get here? 90 minus 25 should be 65, right? 65 degrees. And it is more like a parallelogram. So it is a parallelogram, not more like. So here should also be 65 degrees. Okay? So we get that. Perfect. So we get all the angles here added should be how much? 360 degrees. So it's 360 minus 2 times 65. Because we already know this 2. Okay? 2 times 65. Why do we divide by 2? Because here and here should also be equal. Okay? So whatever is left here and here should also be equal. So here is 115 degrees and here is also 115 degrees. Okay? So that is how we get this 115. Alright, any questions? I guess should be fine. Okay, so that's how the angle here (115 degrees) came about. Okay. Okay, so now to find the value of FR, what do? Just use the cosine law, right? So the value of FR okay, so by just using this, we can get this right. So that is F1, F2 minus 2 times F1, F2 cosine of FR. That's the angle, which is 115 that we already got over there. And then once you substitute that, you can easily get this value. So which is 212.6 can be rounded up to 213. Okay, and once you obtain that, now we apply the law of cosine to determine theta. We want to find the angle. Okay, so here we want to find this angle. Okay, so 150 here corresponds to this angle, right? 150 over sine theta should be equal to FR, we already know, 212.6 divided by sine 115. So now the only one variable we have is sine theta, right? So we will just can easily find this angle. It's equal to 39.8. Okay? So we know that this value here is 39.8. But the 39.8 is from here to here. If we want to know the location of our resultant from the horizontal, what do? We just add this to 15, right? So that's this 39.8 plus 15. And that's how this one came about. Okay, so another very important thing is like when you calculate the direction, you need to tell the professor or the one who is responsible to check your assignment or your solution. You say 54.8 degree from where? So that's why when you solve your solution, it is important to state this. Okay, from the horizontal, measured from the horizontal, measured from the vertical. Okay, if I'm the one supposed to check your assignments, if I'm in a happy mood, I'm like, oh, the person just forget. So, okay, next time. If the person is not in a good mood, oh, you mean 58.4 from the vertical? No, that's not right. So, just do yourself. It's quite easy. Try to remember like the basic steps, okay? The whole process is quite straightforward. It's not that complicated. Okay, so do we have any questions here? No? It's okay if there's anything you don't understand, we can take our time to go through it and then make sure that everyone gets a good understanding, because if you don't fully understand this part, then it's going to be a little bit more difficult for you to understand the later parts we will do it. Okay, so earlier we already mentioned like how we can use the combination of two forces to obtain our resultant force. And now what we are going to do is that we want to use the resultant force to find the components. Okay, so let's say here we have the resultant force of 600 Newton, and then the component forces are acting on this and this. So we want to obtain this and this. Okay, so it says in the component, resolve the horizontal 600 Newton force in figure 2-12a into components acting along the U and the V axis, and determine the magnitudes of these components. So we need to determine the magnitude of the component forces. Okay. Newton, and we have one component here and another component here. So it's U and V. Okay, so similarly, this problem can also be represented as this, just the same way it is over there. You can easily just, you have this U component and the V component, and you assume, okay, this one is going this way, this one is pointing this way, our resultant is this way, so you just move the V over to here. right? And okay, here we assume this is 30, and then the opposite here should also be 30, right? And then we have an angle of, but the difference between, oh, here is 30, here also is 30 degrees, and 120 plus 60, oh yeah, 180. Yes. Okay, so everything from here to here should be 180. We have 30, 30, so from here to here should be 180 minus 60. So that's how the 120 here came about. And then this one are alternate angles. So if this is 120, that means here also should be 120. Okay, so that's how the 120 here came about. Okay, so that's how the okay, so I think the rules for working with angles, if you forget them, please go back and revise them, because if you forget the rules like alternate angles, opposite angles, then it will be really difficult for you to solve this problem, because these directions and angles will not be given to you. You have to rely on your intuition and what you learned from the past. How do I solve angle problem? Okay, these and these are alternate angles. They should be equal, or this and these are opposite. Okay, so please, if you forget, go back and try to remember how to work with angles. Okay, so here we have this 600. We have this. We have this. We also know this. Okay, so if this is 30, this is 120, we can easily know this, right? Because everything here should be 180. Okay, so 120 plus 30, that's 150. So we are only left with, so here also is 30 degrees. So we have this, we get this angle, we have this, so we are only left with this two that we don't know, the magnitude of this and this. Okay, so once we have this, we just apply the same principle, and then we can easily get the solution. Okay, so because we already know the resultant force, so we don't need to use the cosine rule to try to find the resultant force. So what do we need to do? We just use the sine rule to find the magnitude of the component forces, right? So where did I go? So here we know that Fu over sine 120 so we know that Fu over right, based on the sine rule, you know that is the relationship. So we can easily, okay, Fu over sine 120 should be 600 over sine 30. And then we just use that, and then we can find the Fu, that is the U component of our force. And then for the Mv, we just say Mv over sine 30 should be equal to this, right? So this and this will go up. So FB is still equal to 600 Newton. Alright, so for this part, I think the most important thing is that to understand is working with the angles. If you are comfortable with the angles, then the problem should be quite easy for you. But if you find it hard to work with the angles, please go back and try to get accustomed to it. Otherwise, if you don't do it yourself, even if you try to copy the assignments from someone else, when it comes to the exam, it will be really, really, really hard for you to solve the problem by yourself. It might seem easy, but you just need to do it a few times to get used to it. Okay, so here it says, but the result for F shows that sometimes a component can have a greater magnitude than the resultant, okay? So it says sometimes a component force can have the greater magnitude than the resultant force. And then typically it may also depend on the location of the component force. If the component force is like all the way up, then it may have a larger magnitude than the resultant force. But if they are all very close, for example, if they were all like this and this, it will be hard for the component force to be larger than the resultant. But if one component is here and another one is here, then it's most likely that one of the components can be larger than the resultant force. Okay, I think we can just go through this one example, and this other part maybe next week, so I'll just do this. Just do this example, and then we can call it a day. Okay, so here we have another one. It says determine the magnitude of the component force F in figure 2-13A, and the magnitude of the resultant force if Fr is directed along the positive y-axis. So it is telling us that the resultant should be here, along the positive y-axis, right? So if it is along the positive y-axis, what can we do? We can easily just move this to here, okay? And then we can have a triangle, and then we can easily use the triangle law to solve the problem. And because our resultant now is along the y-axis, if this is 30, then we directly know that this should be 60, right? Because it's a 90-degree angle, right? And this already tells us it makes an angle of 45 degrees with the resultant force. Okay, it only has an angle of 45 degrees with the resultant force. So that is also already here. You move it here, you still know it has an angle of 45 degrees with the resultant force. Okay, you have your 45 degrees, so you can easily capture the remaining values from here. And if you want to work it out in another way, it's like, okay, here we have 45, they say, okay, we draw the line, okay, this is also the horizontal x-axis, right? This and this are parallel. They are opposite angles, alternate angles. So if this is 30, then this also should be 30. If here is 45, you draw your line here, here is also 45, right? This and this are also alternate angles. So that's why they have the 30 and the 45 here. But if you can just find this and this, then maybe you just don't need to do this. You can just directly subtract those two from under here and then get it. Okay? So this component is 200. We get this. We know this angle, we know this, and we know this. So what do we need to do? Okay, so let's see. We first have to use the sine rule, because the reason why we cannot directly use the cosine rule here is that we know the value for this, but the value for this is not given. So if you want to use the cosine rule to find this is still missing. So it cannot yield any result. But for the sine rule, what we need is this over this should be equal to this over this should be equal to that over that. So we can still use the sine rule to find the magnitude for each of their forces, okay? So F over sine 60 equal to 200 over sine 45. Okay, so we know this component force is 245. Okay, the component force F is 245. And then for FR, the resultant, FR over sine 75, that's the angle directly opposite it, should be equal to 200 over sine 45. So we get the FR, that is the resultant force FR, okay? And yeah, pretty much does it. And you can see here also is typically the same problem. If you go through it, you can just find the same solution. Okay, so I think the next class should start from the addition of a system of coplanar forces. We can leave that for next week. If we have no other questions as to what we did today already, then the class will stop here for today. You have a good day.